Okay, hello everyone. It's a pleasure to be here. Thanks for the introduction. Actually, this kind of follows on nicely enough from what John was talking about. Even though John focused on air quality, I'm still going to talk about atmospheric particles, but more on the climate side, and black carbon in particular. So this project that I'm working on is really a collaboration between UCC and the University of Toronto, and John Wenger is a co-supervisor on this project. And today I'm going to be talking about the chemical properties, so the chemical composition, but also the optical properties of black carbon particles and the associated climate impacts. Alright, so just a quick background on black carbon. So you saw those filters from the last presentation, that dark colour. You often see these types of emissions from heavy-duty diesel vehicles, for example. Basically, black carbon is soot that you'd be familiar with, and it has a variety of different sources. Okay, black carbon is interesting because it absorbs light across a broad wavelength range. That's why it appears black in colour. And there's really a whole range of different sources. Okay, so any kind of incomplete combustion process can produce this material. So you get sources like fossil fuel emissions, whether it's diesel exhaust, or you can have coal-fired power stations. These can produce black carbon. But apart from the man-made or anthropogenic emissions, there's also naturally occurring emissions. So if you burn biomass in wildfires or forest fires, that can produce huge quantities of black carbon that can have climate impacts. And so black carbon, is particularly important because of this radiative forcing. Okay, so like greenhouse gases, it can have a net warming effect on the atmosphere because it absorbs solar radiation and then re-radiates that heat. So it has a net warming effect on climate. And also there's obviously serious air quality issues associated with black carbon too. So from a health perspective, it's important. So it's an interesting pollutant really, because it contributes to climate change and poor air quality and exposure. But unfortunately, there's high uncertainty associated with the climate impacts. Okay, and there's a couple of different reasons for that I'll get to later. But this graph just shows a breakdown of global emissions of black carbon. This is from a review article by Tammy Bond a couple of years ago at the University of Illinois, and it shows black carbon emissions in terms of gigograms per year, and each bar chart is a different region, and it's kind of difficult to see there, but the different colours represent different sources. Okay, so you can see for different regions that you're seeing very different colours. So for North America in the top there, you can see that vehicle emissions are important, and then if you go to Africa, you see this green bar here that naturally occurring wildfires are very important and produce huge amounts of black carbon that can be transported for days in the atmosphere. And then again, that picture is very different to what you get in East Asia, then, where coal-fired power generation is important, and industrial power generation on site in industrial areas, and also indoor combustion. So people just burning coal at home, a similar problem to what we have here in Ireland, either for heating or for cooking and so on. So depending on where you are in the world, you can be subject to black carbon from very different sources. And a very different mixture of sources. And this graph then is taken from the IPCC report from 2013, and this is the climate relevant properties, okay, the warming impact. So this x-axis here is radiative forcing. So any species that exerts a force here to the right essentially causes positive direct radiative forcing, so it has a warming impact. And on the top here you can see the important greenhouse gases. You've got CO2 and methane. So obviously those are the biggest contributors to the warming effect. And down here then, this region, these are the aerosol species. Okay, so not all of the particles have the same properties. Typically aerosols have a cooling effect. So if you have species like ammonium sulfate in organics, they can scatter light, incoming radiation, and they have a net cooling effect. But black carbon is interesting because this bar goes to the right. Okay, so it's got a net warming effect. It's extremely effective at absorbing solar radiation. But you can see this uncertainty bar here. Okay, that's been associated with this impact is really, really big. Okay, and that's a problem for climate modelling, because we can't really constrain properly what the full impact of black carbon is going to be. Okay. So some of the uncertainty is associated with what are called emissions inventories, so the database that tells the modelers, how much black carbon is coming from each source in each country. There's uncertainties associated with that, but also the actual interaction of light with black carbon particles is another source of uncertainty. Okay, so just trying to figure out how efficiently black carbon absorbs light, which sounds easy, actually creates a bit of a headache for these climate models, because these particles have an unusual shape, and that's something that we'll see next. Okay, so this is what they look like. You saw those black filters from earlier on from Killarney or Enniscorthy, and really, up close, this is what a black carbon particle looks like. They can be quite small, about 100 nanometers across, but they're actually kind of aggregates, right? So they contain lots of these little smaller spherules here, and independent of the source, it's all incomplete combustion. So some carbonaceous material or fuel is burned, and it's not converted to CO2 completely efficiently, so we get these soot aggregates instead. Okay, so this is what black carbon looks like if it doesn't have any coating on it. This is like bare soot, essentially, and this can absorb incoming solar radiation. Okay, across a broad wavelength range, across all visible wavelengths at least. But black carbon doesn't stay like that in the atmosphere. Okay, so black carbon can undergo processing. Because the particles are small, they can be transported for very long distances. They can last in the atmosphere for 5 to 7 days even, and during this time they interact with atmospheric gases that can coat them. Okay, so they can take up organic vapors, or they can accumulate other inorganic species associated with fossil fuel combustion, like sulfate and nitrate, and this kind of swells the particles to larger sizes. Okay, so this particle might have been 100 nanometers at the beginning, but after a few days in the atmosphere, this can grow to be about 300 nanometers across. So these particles can change quite a lot in transit. And so when a black carbon particle is coated like this, assuming that the coating is clear, then it can still absorb solar radiation, okay, which is fine. But me theory suggests that we should also see some refraction. Okay, so this is included currently in climate models. The idea is that the same black carbon particle, if it has a coating around it, will actually experience more solar radiation per unit mass, because some of the light is focused in. Okay, so we've got more photons interacting with the same mass of black carbon, and this has been estimated to contribute an extra 50 or even 70% warming per unit mass, but that's assuming that this is what the particles look like. Okay, that you have a nice kind of core shell structure, that all the black carbon is in the middle, and you have a nice spherical coating around the outside that's transparent, and that can focus the light in. Okay, but the problem is that field studies are giving very different results. Okay, so even when we know that there's coated black carbon around, we don't seem to be able to absorb this or observe this additional absorption that we expect from the refraction of light. So this is important for climate models to get this right, so that we can understand when black carbon is mixed with other species, how much of a warming effect it has on the regional scale. So that was something that we wanted to look at in the field. So the motivation really for this study was to look at mixed black carbon particles, to investigate these coatings and the cores, and to see whether this absorption enhancement is happening in reality. Okay, so people have observed this effect in the lab. If you generate some fresh soot in the lab and coat it with organic material, people have observed enhancements, but the field data, the results vary quite a lot actually. So we wanted to know if we could observe this effect in Toronto in an urban environment. Okay. So we did a campaign in Toronto in 2013. It was really the main focus of the collaborative project was to deploy the instrumentation here and to assess black carbon properties. So the university site is here on College Street, so it's kind of on the edge of this downtown area. So obviously, it's a post-industrial city, so vehicles would be really the major source, or we were expecting vehicles to be the major source of black carbon. We don't expect a lot of industrial emissions or power generation or anything like that. So we just wanted to use instrumentation to investigate black carbon locally. So this is all the gear in the lab. This instrument here is an etophemus, so identical to the instrument that John described earlier for looking at a single particle composition. This instrument here, this is a photoacoustic soot spectrometer. So this measures absorption, and it does that at 2 wavelengths, because we're interested in how much light black carbon absorbs. And then this instrument here, this is another aerosol mass spectrometer. It's called an SPAMS, a soot particle aerosol mass spectrometer. And this looks at black carbon composition. Okay, so it measures concentrations. So we know in micrograms per meter cubed how much black carbon is there, but also it tells us the composition of the coating material. Okay, so it gives us very kind of useful information to try and understand the shape or the morphology of black carbon. We also had this PTRMS instrument on loan from Environment Canada. This actually measures gas phase organics, so I won't be talking about those today, but that's kind of everything in the lab there. This is a thermal denuder, and I'll get back to that in a minute. But really it's these 3 instruments that I'm going to be talking about, or results from these 3 instruments. The first is the photoacoustic soot spectrometer. So that's useful because it measures absorption directly, so aerosol absorption at 400 nanometers and at 781 nanometers. Okay, so we can see if the absorption is wavelength dependent or not. Then the second instrument, the SPAMS, that's for the chemical composition, so that gives us the black carbon concentrations, but also it gives us the concentrations of the coating material, so that we can assess whether black carbon, is internally mixed with other species. And then finally the ATOFMS that John showed the schematic of earlier. This measures a single particle composition and mixing state, so this can be very useful to help us identify sources of black carbon, for example, and to try and pick out whether there's tracers present that can give us some information about where the soot is coming from. Okay, so this was the setup. It's a pretty straightforward idea, really. I mean, what we want is we want to assess the properties of black carbon that we observe in the field. So the ambient soot that's observed out in the street, outside College Street, we look at the optical properties of this one, and then just pass the particles through a thermal denuder, which is at 250 degrees centigrade, to evaporate off the coating, essentially, so get that out of the way, and then just measure the absorption efficiency of the soot again. Okay. So if we see any difference between, the absorption efficiency of this black carbon and this black carbon, then we know that it must be coming from the coating, okay, that the coating is refracting some of this light in, is making the black carbon more efficient, okay, at absorbing solar radiation. And so a difference between the absorption efficiency from the left and right, that's what we're looking for. That was really the purpose of the campaign. And so these are some results. This plot is kind of busy, there's a lot going on, but this is really the chemical composition, okay. This is the chemical data that we get from the SPAMS instrument. So just looking at the top graph first, this is the date here, okay, and the x-axis. So this is how the concentrations are changing as a function of time. And the black trace here, this is the black carbon, and then all of the other colors are species that are coated on black carbon, okay. So you can see that even in Toronto, we're close to the source, that this black carbon has a lot of material on it, even when it's very fresh. Okay, so that was one thing that surprised us. It's not really representative to even think about black carbon as being uncoated at all. We almost always see at least organic material internally mixed with the black carbon. So this green here, this is organics, and that can be a whole range of different organic compounds that have condensed on black carbon. And then at times you can see these other colors. This blue, this is nitrate, and red is a sulfate. So at times we also have some inorganic material in the shell of the black carbon particle as well. Okay. Also, you see the concentrations change a lot as a function of time. We have these events sometimes where we've got much higher concentrations. And finally, the last kind of piece of data that's on here is this purple dashed line. Okay. And what's that's showing is that it's the mass ratio of the coating to core for these particles. Okay, so if this purple line here is high, it means we've got black carbon that has really a lot of coating material on there. Okay, so we kind of see that there's different periods during the campaign where the composition of the black carbon is very different. So we've got some smaller particles here with a thin coating, and then we have times where we've got these particles with an enormous coating, and so we're expecting maybe some differences in the optical properties for these different periods. Then the bottom panel is actually, it's just the same data, just graphed in a different way, so that all the composition just adds up to 100%. And you can see there's times when the particles are about 40% black carbon, and then there's times when they're only about 20% black carbon when they've got very thick coatings. And I'll come back to the different periods later on in the talk. But yeah, it looked like we had perfect conditions to try and find any unusual absorption behavior, just because we were seeing a lot of different types of black carbon particles during the campaign. So these are the optical results from the photoacoustic instrument. Okay, so there's 4 panels here. The ones on the left, these blue data, these are the 405 nanometer light, and the red data are 781 nanometers. And really what we're looking at is the absorption efficiency of black carbon, of this material. So the x-axis in each case is the concentration, the mass concentration in air. So this is black carbon in micrograms per meter cubed. And then the y-axis is the absorption data from the PASS instrument. So we can look at absorption per unit mass under different conditions. So the top 2 graphs, this is just the ambient data. So these are like the coated particles essentially. And then the 2 panels at the bottom, this is after passing the black carbon through the denuder. So we've removed the coatings, and then we look at the absorption efficiency per unit mass again, essentially, and compare it. So if you look at the red data here on the right, you can see that at 781 nanometers, you can see the slopes here are very close, okay? So this is the absorption efficiency for this guy, this is the absorption efficiency with no coating, and the slope is 3.05 here, and the slope is 3.08 here. So there's actually not even a statistically significant difference between these 2 data sets, which suggests that for this longer wave radiation at 781 that there's no impact actually. Whether you have this coating or not, that there's no evidence for any lensing. There's a little bit of a difference for the blue light. Okay, we can see that the slope here is 7.2 and the slope here is 8. So there's a possibility that across the campaign on the whole, that seems that maybe we've got extra absorption for these coated particles, and so that's something that we wanted to look at in more detail. So this is just a box plot of our absorption enhancement. So really, the y-axis here, this is just the ratio of how much extra absorption there is relative to for a coated particle relative to the uncoated one. So basically, if there was no enhancement, your data would be on this line 1 here, which is actually what we get at 781 nanometers, which suggests that there's really nothing exciting, happening here in terms of lensing or refraction. But for the blue light, there was, the mean is about 12% here. It's this an absorption enhancement that we didn't really expect. And this is statistically significantly different than the uncoated data. And so we wanted to look then at different times during the campaign to see if, is there a certain type of black carbon that produces this extra absorption. Okay. And we also wondered, of course, why the enhancement is wavelength dependent, okay, because that's not something that we were expecting. So this term, this Angstrom exponent, the absorption Angstrom exponent, really just describes sort of like the absorption spectrum for black carbon. Okay, it's really the curvature of this line here. Okay, so how the absorption efficiency of the material changes as a function of diameter, or is dependent on diameter. So we've got wavelength at the bottom here, and you see you get this kind of gentle slope here for black carbon. It's got an Angstrom exponent value of 1. Okay, so as we go to longer wavelengths, it absorbs less efficiently. Okay? And according to meat theory, if you coat those particles with a clear coating and we get an absorption enhancement or this refraction of light, that should be pretty consistent across all wavelengths. Okay, so this edge of the graph here, this is kind of our 781 nanometer area that we were looking at with the photoacoustic instrument, and then the other wavelength was down here, the blue light at 405. So we would have expected to see absorption enhancement at both wavelengths. Okay, so we should have seen an enhancement here, and that's not what the data are showing us. We get a picture that's more like this. Okay, that's more consistent with brown material or brown carbon, and that's a type of organic aerosol that absorbs light more efficiently, at shorter wavelengths. It's typically associated with biomass combustion or wood smoke combustion. And this curvature here of the Angstrom exponent is the basis for the source apportionment using the 8-kilometer instrument that John and Ian and Owen and Jovan are using for their campaign. You can try to separate wood burning emissions from diesel vehicle emissions using this curvature. So that was interesting. It appears that we've got brown material at some point during our campaign. And so we decided to just split it up into different periods and kind of see where the sources might be, because there was clearly, you know, periods that have very different black carbon particle compositions going on. Okay, so separating it up into periods was useful for us to examine the meteorology. So to do this, we got some help from a group in Norway, André Stoll's group at NILU, and they generated these plots for us. Okay, it's kind of difficult to see in this one, but Toronto is basically in the middle of this dot here, and what the colours are showing you are kind of the history of the air that's arriving at the site. Okay, so they show you like the geographical origins of the air coming in, you know, so where this air might have been susceptible to emissions outside of Toronto. So period 1 was really dominated by local emissions. So you can see there's this hot spot here just around Toronto, and it's kind of, you know, blue or white everywhere else outside the city. And so this is telling us that any of the black carbon that we see during this period we expect to be coming from the city, coming from Toronto, most likely traffic emissions. And then during period 2 things are very different. Okay, so we have this fast-moving air mass that comes in from the Arctic, okay, and it passes through Quebec before arriving in Toronto. And you can see that there's these warm regions here where this air was susceptible to ground-level emissions, you know, quite a long way out and far away from the city. And there's these tiny black spots here, okay, and what these black spots are, these are wildfires that have been identified using the MODIS satellite. So the satellite data to identify when wildfires are occurring, and you can see we're really in that zone there where the air is kind of passing over these wildfires and bringing emissions to Toronto. Okay. Finally, the third period is different. Here we're getting the influence of emissions from the United States. Okay, so the air kind of shifts again. There's a lot of power generation here in the Ohio Valley. You've got a lot of fossil fuel emissions, so we see very different type of black carbon during this period that has those inorganics in there, the nitrate and sulfate. So splitting it up into periods was useful because then we could look at how the composition was different for those different periods. Okay, so this one on the left, this period 1 was like the local emissions. So these black carbon particles, you know, they've got a lot of black carbon by mass with some organics. They're mostly associated with traffic. And then down here, this last graph, this is the composition, but as a function of diameter. Okay, so the SPAMS instrument can do that for us. It measures the diameter of the particles too, and you can see that there's 2 types of black carbon particles. You've got these little ones, okay, that are about 100 nanometers, and they have kind of thin coatings. Typically, you know, organic material likely associated with lubricating oil, and then we have some aged larger ones that have a bigger diameter and, you know, much more coating material. But then things change completely when we went to this period 2. Okay, you can see that during this period we still have the little particles, the small black carbon ones, but really these ones are dominating now. We've got particles that contain a black carbon core but have, you know, a huge organic coating, and you can see really that the organics really dwarf the black carbon here. They're really kind of the majority of the composition. And then finally, during period 3, we have these United States emissions that contain, you know, inorganic ions, and these are all quite large as well. Okay, all about 400 nanometers in size. And so this should be really the ideal conditions to observe this lensing effect that I mentioned earlier. I mean, we know we've got, you know, black carbon cores. We know we have these enormous coatings, so we should at least see some effect. But that doesn't seem to be the case at all. Okay. So also, it's worth just looking at the optical properties then for those 3 periods separately. And this is the data on the right here for the 781 nanometers. I showed this earlier. The y-axis is the absorption enhancement. And so for each period, you know, it doesn't matter where the black carbon is coming from. It doesn't matter how big the coatings are on it. There is just nothing happening here. Okay, nothing exciting happening in terms of extra absorption. Okay, so it appears that the coatings aren't focusing any extra light onto black carbon, at least, you know, for this field campaign. But the interesting thing is that at 405 nanometers, it's very different. Okay, we do get an absorption enhancement, but it's not optical lensing. It's just brownness. Okay, so we've got particles that are brown, so they can absorb light efficiently at 405, but not at 781. Okay, so what we're getting is when we get the wildfires basically influencing Toronto, this wildfire material from Quebec, these particles have large coatings, but the coatings are brown. So that can absorb light more effectively than, you know, fresh organic material that hasn't been oxidized. And the interesting part is that there's actually so much brown carbon present that this can contribute to radiative forcing itself. Okay, so if you forget about the lensing entirely and just think about how much light the aerosol is absorbing, then this material becomes important. Okay, it's not as efficient at absorbing light as black carbon is, but there's just lots of it. There's probably 20 times more of this brown carbon than there is black carbon when we're in the influence of that plume. So this obviously has climate implications too. And just for comparison, okay, I've just added here some of the predicted values. Okay, if we use me theory and you create a core shell structure from the chemical data that we've got, the absorption enhancements that you would expect and that would be relevant for modeling purposes, are on the order of a factor of 2, 1.9 up to 2. So that's an additional 100% more absorption that modelers might expect if they only had this composition data and then used me theory to estimate the warming effect. Okay, so these numbers are essentially way off, okay, for our campaign. And by comparison, at 781 nanometers, this lensing effect, we're just seeing, no impact whatsoever. So the only really interesting aspect from an absorption perspective is that the brown material during period 2 is strongly absorbing at 400 nanometers. So just to conclude, we found that this optical lensing impact is not relevant, okay, for black carbon in Toronto, so we removed the coatings and it doesn't make any difference. However, this direct absorption by brown carbon is relevant when the site is influenced by wildfires, and it can be responsible for up to 50% of direct absorption at 405 nanometers at times. Okay, so it's equally important as the black carbon at times in terms of regional warming. And all organic aerosol is currently treated as purely scattering in climate models. Okay, so there's no absorption taken into account for this brown material. But also the lensing thing is interesting because the radiative forcing estimates using me theory would lead to over predictions of regional warming here and in other locations where the core shell approximation is assumed. So definitely some care must be taken when accounting for this BC black carbon internal mixing state and climate models, and definitely there's more studies like this are warranted to look at different types of black carbon in different locations to try and get better numbers for modelers to constrain their warming impacts. So this for the future. Some other outcomes from the project, we've also been doing some mixing state work, looking at how to better describe the mixing state, how other species are present in the same particles as black carbon, for example, and also to try and use single particle chemical data to better predict other climate relevant properties like new cloud formation and how much particles will grow under high humidity conditions. And finally, the last thing that we're working on is to develop a library of single particle data, and that would include this ATOPMAS data collected here in Ireland, also representative of different sites, to try and generate a data set that other groups can use to help with their analysis in other locations. So finally, I'd like to thank all my colleagues at U of T, and also Andreas Stoll's group at NILU in Norway, and in particular John Wenger for his supervision on the project. And I'd like to thank you all for your attention.